In the summer of 1950, 4 physicists were walking to lunch at Los Alamos National Laboratory. They'd been talking about a cartoon, a silly New Yorker cartoon about flying saucers, and the conversation had drifted, the way lunch conversations between physicists tend to drift into bigger and stranger territory, into the question of whether alien life might actually exist somewhere out there, and if it did, why we hadn't seen any sign of it. 3 of the physicists offered opinions, estimates, guesses, and then the 4th one, somewhere in the middle of a conversation about something else entirely, suddenly looked up and said, "But where is everybody?" That was Enrico Fermi, Nobel Prize winner, one of the architects of the atomic age, a man who had spent his career thinking precisely and carefully about problems that seemed impossibly large, and those 4 words, "Where is everybody?" are the most productive and the most haunting question in the history of science. We have been living inside that question for 75 years. We have launched radio telescopes into orbit and pointed them at the sky for decades, listening for a signal. We have catalogued thousands of exoplanets, including hundreds of Earth-sized ones in the habitable zones of their stars. We have found organic chemistry everywhere we look in the universe, in the clouds between stars, in meteorites, in the atmospheres of distant planets. We have found liquid water, or the conditions for it, in more places in our own solar system than we ever expected. We have pushed our understanding of how life can emerge and survive to extraordinary limits, and we have heard nothing, seen nothing, found nothing. The silence has held, but here's what's changed. In the last 3 years, and I want to be very specific about this timeline, because the pace of discovery has been genuinely extraordinary. A series of observations, experiments, theoretical models, and data analyses have come together in a way that has the scientific community doing something they very rarely do publicly: reconsidering. Not abandoning the question, not claiming they've definitively solved it, but reconsidering, in a serious and methodical way, whether the Fermi Paradox is actually as paradoxical as it seemed, whether the silence is genuinely mysterious, or whether we've been making assumptions that, when you scrutinize them carefully, don't hold, whether the question, "Where is everybody?" has an answer, and whether that answer is something we are psychologically prepared to sit with. Because here's what I'm going to argue in this video. The Fermi Paradox is one of those problems that feels like it should have a single dramatic resolution, a discovery, a signal, a first contact event, something that crosses the finish line and gives you the answer. And maybe it will. Maybe JWST is going to find biosignatures in some exoplanet's atmosphere next year, and the question changes overnight. That could still happen. But what the last 3 years of science suggest is that the Fermi Paradox might not need a dramatic resolution. It might already be dissolving, quietly, through accumulated evidence, through the patient work of scientists who have been doing the math more carefully than their predecessors, who have been measuring things we couldn't measure before, who have been building models with better data, and finding that the assumptions underlying the paradox are wrong in ways that are simultaneously less exciting and more interesting than a radio signal from a distant civilization. We may, in fact, be close to solving it, not with a bang. With a long, careful, uncomfortable look at what we actually know, let's go through it, all of it. The original paradox, the classical solutions, the ones that feel compelling but don't survive scrutiny, the new evidence, the new math, the uncomfortable possibility that sits at the end of all of it. Let's start from the beginning. Chapter 1. The silence that shouldn't exist. To understand why the Fermi Paradox is such a profound problem, you have to start by really sitting with the numbers, not in a hand-wavy, the universe is really big way, but in a specific quantitative way that makes the silence genuinely astonishing. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Let's use 200 billion as a reasonable middle estimate. Of those stars, recent data from the Kepler Space Telescope and subsequent exoplanet surveys suggest that approximately 20% to 30% of Sun-like stars have an Earth-sized planet in their habitable zone, the orbital distance range where liquid water can exist on a planet's surface. If we extend that to all star types, including the very common red dwarfs which make up about 75% of all stars in the galaxy, the fraction of stars with potentially habitable planets may be as high as 40%. Let's be conservative. Let's say 10%, That still gives us 20 billion potentially habitable worlds in the Milky Way, 20 billion in a single galaxy, our galaxy alone. Now let's talk about time. The Milky Way is about 13.6 billion years old. Our solar system formed about 4.6 billion years ago, meaning there were stars, and potentially habitable planets, in this galaxy for nearly 9 billion years before Earth came along. The oldest Sun-like stars formed roughly 10 to 11 billion years ago. If life emerged on any of the planets around those early stars on a similar timeline to how it emerged on Earth, roughly a billion years to get going, a few billion more to develop complex multicellular life, then the first complex life in the Milky Way could have emerged 6 to 7 billion years ago. And if that life developed technology, radio communication, spaceflight, the capacity to modify its environment on large scales, it would have had a head start of billions of years on us. Billions, not millions, not thousands. Billions of years during which, if a civilization chose to expand or explore, it could have colonized the entire Milky Way galaxy many times over. Here's the math on that. The Milky Way is roughly 100,000 light-years in diameter. If a spacefaring civilization expanded at even 1% of the speed of light, which is not particularly fast by the standards of what physics permits, it would take roughly 10 million years to colonize the entire galaxy. In 6 billion years, a civilization could have colonized the galaxy 600 times over, even at that modest speed. Even without physical colonization, the timescale for signals to propagate across the galaxy is 100,000 years. A civilization broadcasting radio signals for 1 million years, a blink in cosmic terms, would have had signals reaching every corner of the galaxy and bouncing back multiple times. In 6 billion years, the galaxy should be, by any reasonable extrapolation of the current trajectory of Earth's own development, completely saturated with the presence of intelligent life. Every star system should either be inhabited, visited, or at minimum be receiving electromagnetic broadcasts from dozens of civilizations. The sky should be loud with signals. We should be swimming in evidence of intelligence. And we are not. That is the Fermi Paradox. Not, we haven't found aliens yet, which would be trivially explainable by the limitations of our detection equipment, but rather the far deeper problem. The numbers say that if even one civilization in the galaxy's history had developed the capacity and desire to expand, we would know about it by now. The silence isn't just surprising, it's mathematically inexplicable, or it should be. But there is a subtler and in some ways more disturbing version of the Fermi Paradox that goes beyond the colonization argument. Even without physical expansion, even without any civilization choosing to send ships to other star systems, a technologically advanced civilization conducting ordinary activities, running a planetary-scale industrial economy, transmitting communications, launching satellites, generating waste heat, would produce observable signatures. We call these techno-signatures, and they span an enormous range of possible detection methods. A civilization at Earth's current level of technology, running for 10,000 years, would by now have produced enough radio leakage into space to be detectable within a few hundred light-years with technology comparable to our own radio telescopes. A civilization at a higher level of technology, say one that had mastered fusion power and built large structures in orbit around its star to capture solar energy, would produce infrared signatures detectable across thousands of light-years. A civilization that modified the chemistry of its planet's atmosphere through industry would produce spectroscopic anomalies visible to observatories like the James Webb Space Telescope at distances of tens to hundreds of light-years. None of this requires a civilization to be trying to make itself known. It just requires them to exist at a technological level somewhat above ours. The byproducts of civilization are, on cosmological scales, detectable. Our own leakage radiation, the total output of our radio and television broadcasts, our radar systems, our satellite communications, is already a faint but real signal propagating outward from Earth at the speed of light, announcing our existence to whatever might be in the cosmic neighborhood. The Voyager probes launched in 1977 are still transmitting. Their signals, a few watts of power, less than a flashlight, are detectable with our best radio telescopes from the outer solar system. A civilization 100 light-years away with telescopes significantly better than ours could, in principle, detect our existence from our radio leakage. In another century, As our communications technology continues to develop and our observable footprint expands, we will be increasingly visible. The question is, who else should be visible to us? The astronomer Frank Drake formalized this intuition in 1961 with what became known as the Drake equation, a mathematical framework for estimating the number of active communicating civilizations in the galaxy at any given time. The equation takes the form of a product of several factors: the rate of star formation, the fraction of stars with planets, the fraction of those planets that can support life, the fraction where life actually emerges, the fraction where intelligent life emerges, the fraction of intelligent species that develop detectable technology, and the average lifespan of such technological civilizations. The Drake equation is not really an equation in the sense of producing a precise answer. It's a framework for organizing ignorance, a way of identifying which factors matter and which are most uncertain. When Drake first ran it at the famous Greenbank Conference in 1961, he estimated there might be anywhere from 1,000 to 100 million communicating civilizations in the Milky Way right now. The enormous range reflected genuine uncertainty, not imprecision in the math. Over the decades since then, our knowledge of some factors in the Drake equation has improved dramatically. We now know that planets are common. The fraction of stars with planets is close to 1. We now know that Earth-sized planets in habitable zones are common, probably tens of % of Sun-like stars, possibly more for red dwarfs. We now know that the basic chemistry of life, amino acids, nuclear bases, organic molecules, forms readily in space under ordinary physical conditions, making the building blocks of life ubiquitous. The factors we still don't know, the fraction of habitable planets where life emerges, the fraction where intelligence emerges, the average lifespan of technological civilizations, remain deeply uncertain, and they remain the crux of the paradox. But here's what makes the Fermi Paradox particularly vexing. The Drake equation doesn't need most civilizations to produce observers. It only needs one civilization anywhere in the galaxy's 13.6 billion year history that developed the capacity for galaxy-scale influence and chose to exercise it. That's all it takes. And the mathematics says that in a galaxy this old with this many potentially habitable planets, the probability of not even one such civilization emerging is, under standard assumptions, vanishingly small. Carl Sagan estimated in his popularizations of the Drake equation that there should be roughly 1 million communicating civilizations in the Milky Way right now. 1 million! If even a fraction of a % of those had ever developed the motivation and capability to colonize beyond their home star system, the galaxy should look fundamentally different from what we observe. So something is wrong. Either the optimistic assumptions in the Drake equation are wrong, life is far rarer than the chemistry suggests, or intelligence is far rarer than life suggests, or technological civilizations are far shorter lived than we hope. Or we've made an error in our reasoning about what an expanding civilization would look like, or how detectable it would be. Or there's something else happening, something we haven't fully modelled, that explains the silence. There is one thing worth noting about the history of SETI, the search for extraterrestrial intelligence, before we move into the proposed solutions, because the history of that search is itself instructive, both in what it has found and in what it hasn't. SETI began in earnest in 1960, when Frank Drake pointed an 85-foot radio telescope at a nearby Sun-like star and listened for signals on the hydrogen line frequency, the frequency at which hydrogen atoms emit and absorb radio waves, the most common element in the universe, the frequency that a civilization attempting to make contact might logically choose. He heard nothing conclusive, but the experiment established a methodology, and SETI has been running in various forms ever since. The most famous moment in SETI history is the WOW signal, a 72-second radio burst detected on August 15th, 1977 by astronomer Jerry Eman at the Big Ear Radio Telescope in Ohio. Eman circled the printout of the signal and wrote "WOW" in the margin. The signal was precisely what a transmission from an extraterrestrial intelligence might look like. It appeared at the hydrogen line frequency, it had the correct bandwidth profile, it came from a fixed point in the sky, rather than from a moving terrestrial or orbital source. It was never detected again, despite repeated attempts to observe the same region of sky. The WOW signal remains the most intriguing candidate signal in 65 years of SETI research. It also remains unexplained. A 2017 paper proposed it was caused by a hydrogen cloud surrounding a pair of comets passing through the field of view. Other researchers have challenged this explanation. The honest answer is, we don't know what it was. It might have been a natural phenomenon, it might have been interference, and it might have been something else, something that broadcast for 72 seconds and then went silent, and we have been unable to catch it again. 65 years of listening, one unresolved anomaly, everything else, silence. The Breakthrough Listen initiative, launched in 2015 with $100 million in funding from Russian entrepreneur Yuri Milner, has brought unprecedented observational power to the SETI question. Using the Green Bank telescope, the Parkes Observatory, and the Meerkat array, it has conducted the most comprehensive radio searches ever performed, covering more of the sky, more of the frequency range, and more of the possible signal types than any previous effort. It has also conducted optical SETI, searching for laser pulses, which might be a preferred communication technology over radio for advanced civilizations. So far, nothing confirmed. Some anomalies, some interesting signals that didn't survive follow-up observation, some statistical curiosities, but no confirmed signal. 65 years, increasingly powerful instruments, increasingly comprehensive searches, and still silence. The search for that something, that explanation for why the galaxy isn't crawling with detectable alien presence, has produced a remarkable diversity of proposed solutions. Some of them are optimistic, some of them are deeply pessimistic, some of them are bizarre, and in the last few years some of them have gotten a lot more specific, a lot more testable, and a lot more uncomfortable. Let's go through them. Chapter 2. All the wrong answers. Before we get to what scientists are now saying might actually be the resolution of the Fermi Paradox, it's worth understanding why the classical proposed solutions mostly don't work. Because the history of proposed answers to Fermi's question is itself fascinating, and it's in the failure modes of those answers that you start to see the outline of what a real solution might look like. The proposed solutions can be roughly divided into two categories: those that say aliens exist but we can't detect them, and those that say aliens essentially don't exist, or exist in such small numbers that we shouldn't expect to have found them. Let's go through both. The zoo hypothesis. This is probably the most psychologically comforting of the proposed solutions, which is one reason people keep reaching for it despite its serious problems. The zoo hypothesis proposes that intelligent extraterrestrial civilizations are aware of us, or aware of Earth as a potentially developing world, and have chosen not to make contact. They're watching us from a distance, the way wildlife researchers observe animals in the wild without intervening, waiting for us to reach some threshold of development before revealing themselves. There are versions of this that involve a galactic federation with a no contact policy for pre-spacefaring civilizations. There are versions that invoke a kind of cosmic quarantine. There are versions that sound uncomfortably close to the plot of Star Trek. The zoo hypothesis fails on a simple logical point that its proponents have never adequately addressed. It requires unanimous consensus. If there are thousands or millions of civilizations in the galaxy, it requires that every single one of them, for billions of years, maintain a perfectly consistent policy of non-contact with Earth. Not one defector, not one rogue actor, not one civilization that disagrees with the policy and breaks it, not one alien equivalent of a scientist who thinks that making contact with a developing civilization would be worth the ethical complications. The uniformity required by the zoo hypothesis is not just unlikely, it's essentially impossible to maintain over cosmological timescales among a large population of independent actors with different values, different motivations, and different histories. The zoo hypothesis requires an interstellar consensus more perfect and more durable than any that has ever existed among any group of humans for any period of time longer than a few decades. It doesn't hold. The "they're all dead" hypothesis. The slightly more sobering version of the Fermi resolution is that civilizations like ours are common enough. Life is common, intelligence emerges regularly, but that they inevitably destroy themselves before reaching the galaxy colonizing stage. Nuclear weapons, climate catastrophe, engineered pandemics, rogue artificial intelligence, or some other self-terminating technology cuts each civilization off before it has the chance to leave its home system. This is the great filter hypothesis in one of its forms, and we're going to spend an entire chapter on it because it's one of the most important and genuinely chilling ideas in this space. But as a simple Fermi Paradox resolution on its own, it has a specific problem. For this to explain the Fermi Paradox, it requires that every technological civilization destroys itself before leaving its home system. Not most of them, not 99% of them, every single one. Because if even 1% of civilization survived and expanded, the galaxy would still look completely different from what we see. And our own history doesn't actually support the inevitable self-destruction narrative as strongly as popular culture suggests. Humanity has had nuclear weapons for about 80 years. We came terrifyingly close to using them. The Cuban Missile Crisis in 1962 was, by the accounts of the people who were in the room, far closer to nuclear exchange than official history has acknowledged for decades. But we didn't use them. We built institutions, treaties, norms. We established hotlines and inspection regimes. We're still here, still accumulating knowledge, still building things. Which doesn't mean we'll make it. But it suggests that self-destruction isn't as automatic or inevitable as the "they're all dead" hypothesis requires. There's also a statistical problem. If technological civilization regularly self-destructs, the distribution of civilizations in the galaxy should show a range of developmental stages, including some that are 50 or 100 or 1,000 years ahead of us, which should be detectable even if the most advanced ones are gone. We don't see that gradient either. The "they're not interested" hypothesis. This one proposes that advanced civilizations simply aren't interested in colonizing the galaxy or broadcasting their presence. Maybe they turn inward, building rich virtual realities, exploring the inner space of consciousness or computational simulation rather than the outer space of physical stars. Maybe they achieve some kind of post-material existence where physical expansion simply isn't meaningful or interesting. Maybe they're there, but they're not doing anything we'd recognize as galaxy colonization, and they're not broadcasting in ways we'd detect. This one is more interesting than the zoo hypothesis, and it's harder to definitively dismiss. We genuinely can't know what values and motivations an advanced civilization would have. It's entirely possible that the drive to expand, explore, and colonize is a feature specific to our current developmental stage, and that more advanced civilizations transcend it. But it runs into a similar problem as the self-destruction hypothesis. It needs to be universal. Every civilization. Forever. Not one in the history of the galaxy that chose to colonize or broadcast or reshape its stellar environment in ways that we could detect. When you look at the diversity of motivations and behaviors within a single species, humans, the idea that every alien civilization across billions of years of galactic history would converge on a stay quiet and turn inward strategy is not obviously plausible, especially given that in any sufficiently large population of actors, a small minority with expansionist motivations would compound their numbers and their reach exponentially, eventually dominating the available space regardless of what the majority were doing. The "we're not looking right" hypothesis. Maybe alien civilizations exist and are broadcasting, but they're using communication methods we haven't thought of yet. Quantum entanglement, neutrino beams, gravitational waves encoded with information, something we don't have the equipment to detect. Maybe our SETI searchers have been looking in the wrong frequency bands, or with the wrong modulation schemes, or at the wrong targets. This is plausible, and probably true to some degree. We have searched only a tiny fraction of the possible search space, but it faces the same universality problem. Why would every civilization use only communication methods we can't detect? Our own technology, developed in a cosmic eye blink, has made radio astronomy detectable from interstellar distances. The same technology that let us detect the cosmic microwave background, black hole mergers, and gravitational waves from neutron star collisions should let us detect, or at least see the byproducts of, industrial civilization on nearby stellar systems. And radio silence isn't the only thing we're looking for anymore. We're looking for Dyson spheres, megastructures built around stars to capture their energy, which would produce distinctive infrared signatures. We're looking for atmospheric biosignatures in exoplanet spectra. We're looking for laser communication pulses. We're looking for industrial chemistry, the products of large-scale manufacturing, in stellar spectra. The range of searches we're conducting has expanded enormously, and we still have nothing. The rare earth hypothesis. This one is different from all of the above. It doesn't propose that aliens exist but we can't find them. It proposes that complex intelligent life is genuinely rare, not just rare by the standards of the galaxy, but cosmically rare, possibly unique. The conditions that produced Earth, the right kind of star, the right orbital location, the right planetary system architecture including a Jupiter analog deflecting comets, a large moon stabilizing the axial tilt, plate tectonics cycling carbon, a magnetic field protecting the atmosphere, may be extraordinarily improbable when considered as a conjunction. Geologist Peter Ward and astronomer Joe Kirschvink developed this hypothesis in their 2000 book Rare Earth, and it was controversial at the time. In the 2 decades since, the exoplanet data has made parts of it seem more compelling and parts of it seem less. The overall picture is genuinely uncertain. We know planets are common, but the specific combination of factors that may be required for complex life remains poorly characterized, the rare Earth hypothesis. This one is different from all of the above. It doesn't propose that aliens exist but we can't find them. It proposes that complex intelligent life is genuinely rare, not just rare by the standards of the galaxy, but cosmically rare, possibly unique. The conditions that produced Earth, the right kind of star, the right orbital location, the right planetary system architecture including a Jupiter analog deflecting comets, a large moon stabilizing the axial tilt, plate tectonics cycling carbon, a magnetic field protecting the atmosphere, may be extraordinarily improbable when considered as a conjunction. Geologist Peter Ward and astronomer Joe Kirschvink developed this hypothesis in their 2000 book Rare Earth, and it was controversial at the time. In the 2 decades since, the exoplanet data has made parts of it seem more compelling and parts of it seem less. The overall picture is genuinely uncertain. We know planets are common, but the specific combination of factors that may be required for complex life remains poorly characterized. It's worth going through the list of requirements in the rare Earth hypothesis in some detail, because each one individually might seem like a quibble, but together they constitute an argument that is harder to dismiss. Start with the star. Earth orbits a G-type yellow dwarf, a medium mass, relatively stable, relatively long-lived star. About 7% of stars in the Milky Way are G-type. The most common stars, red dwarfs, make up about 75% of all stars. Red dwarfs are problematic for complex life for several reasons. They're often highly active in their youth, bathing nearby planets in intense UV and X-ray radiation that could strip atmospheres or damage biology. Their habitable zones are much closer in, meaning that planets in those zones are often tidally locked, one side permanently facing the star, one permanently facing away, creating extreme temperature gradients and atmospheric circulation patterns that may make complex life difficult. They're also low in ultraviolet light, which may have driven the initial development of oxygenic photosynthesis on Earth. Then there's the galactic location. Earth is in the outer Milky Way, in a relatively calm region between spiral arms. The inner galaxy is more densely packed with stars, meaning more frequent exposure to gamma-ray bursts and supernova explosions that could sterilize planetary surfaces. The galactic center is even more hazardous, with its dense star population, intense radiation environment, and supermassive black hole. Some astrobiologists have proposed a galactic habitable zone, a ring-shaped region of the Milky Way at roughly our galactic radius that balances the availability of heavy elements, which require generations of stellar nucleosynthesis to accumulate, with the stability of the stellar environment. Then there's the Moon, Earth's large moon, formed about 4.5 billion years ago when a Mars-sized body called Theia struck proto-Earth and the debris coalesced into our satellite, is thought to stabilize Earth's axial tilt. Without the Moon's gravitational steadying influence, Earth's axial tilt might vary chaotically between near zero and more than 85 degrees over millions of years. Such drastic variations would cause global climate swings that might prevent the development of stable, complex ecosystems. Mars, which has no large moon, has experienced significant axial tilt variations over geological time. Earth's tilt varies within a narrow range, currently between 22.1 and 24.5 degrees, on a roughly 41,000-year cycle that is regular and predictable. Then there's plate tectonics. Earth's crust is broken into moving tectonic plates, driven by internal heat. This tectonic activity cycles carbon between the atmosphere and the deep Earth over millions of years, acting as a thermostat that has kept Earth's surface temperature in a range suitable for liquid water, despite the Sun increasing in luminosity by roughly 30% over the past 4 billion years. The carbonate-silicate cycle, enabled by plate tectonics, may be the reason Earth hasn't frozen permanently or cooked in a runaway greenhouse. And it's not clear that plate tectonics is a common planetary feature. Venus, with roughly Earth's size and composition, has no plate tectonics. Mars had some tectonic activity early in its history but lost it. A planet without plate tectonics might have difficulty maintaining the long-term climate stability needed for the development of complex life. The rare Earth hypothesis is one of the serious contenders for a Fermi Paradox resolution, and we'll come back to it. But it has its own problems. It requires that the conjunction of necessary conditions is so rare that Earth is unique, or nearly unique, in the galaxy. Given that the galaxy contains 200 billion stars and has been around for 13.6 billion years, nearly unique still has a lot of room in it. And the discovery of life anywhere in our solar system, even microbial life, even fossilized evidence of past life, would dramatically reduce the probability that Earth is as rare as the rare Earth hypothesis requires. None of these classical solutions are entirely satisfying. Each one either requires too much coincidence, too much universality, or runs into specific empirical problems that make it hard to accept as the whole answer. But there are newer proposed solutions that have emerged from the last decade of exoplanet data, from advances in astrobiology, from more careful mathematical treatments of the Drake, equations uncertainties, and from a specific chilling philosophical argument that crystallizes what's really at stake. Before we get to the new stuff though, there's one classical hypothesis we've been dancing around, one that deserves its own chapter, because it's the one that has the most serious scientific and philosophical heft, and the one whose implications are most directly terrifying. Chapter 3: The Great Filter and Where It Might Be. In 1998, a young economist named Robin Hanson published a short paper with a deceptively simple premise. He wasn't a biologist. He wasn't an astronomer. He was someone who thought carefully about probability and decision theory, and what he noticed was that the Fermi Paradox, when you stripped it down to its essential structure, implied something specific about the history of intelligent life in the universe. His argument went like this: the universe is roughly 14 billion years old. It is large enough and old enough that, under optimistic assumptions about the frequency of life and intelligence, it should have produced many civilizations capable of galaxy-scale expansion. We see no evidence of any such civilization. Therefore, at some point along the developmental pathway from raw matter to galaxy-colonizing civilization, there must be a filter, a step that is extremely difficult to pass, that most developmental pathways fail at, that explains why the galaxy isn't full of observable intelligence. He called it the Great Filter. The Great Filter doesn't need to be a single step. It can be a combination of low-probability events, each individually possible, but collectively forming an extremely narrow bottleneck. What matters is that somewhere between planet with the right chemistry and civilization capable of interstellar colonization, there's a step, or a set of steps, that almost nothing gets through. And here is where Hanson's argument takes its disturbing turn, because the location of the Great Filter matters enormously for what we should feel about our own future. If the Great Filter is mostly behind us, if the improbable, extraordinarily difficult steps are the ones that got us here, the ones we've already passed, then we might be among the first and rarest forms of intelligence in the galaxy. The filter is mostly in our past. We've survived it. The road ahead, while not without dangers, is not blocked by some civilization-ending wall we don't know about. In this scenario, the Fermi Paradox is explained by the extraordinary rarity of our developmental history, and we might have an open future. If the Great Filter is mostly ahead of us, if the difficult, almost universally failed step is one we haven't encountered yet, then the implications are catastrophic. It means that civilizations like ours, at our current developmental stage, almost always fail before reaching galaxy-scale expansion. Whatever destroys them is ahead of us, not behind us. Something that every technological civilization runs into and almost none survive. The location of the Great Filter is therefore not an abstract philosophical question. It is, arguably, the most practically important question in science, because depending on the answer, we are either a rare miracle or a doomed typical case. So where might the filter be? Candidate filter locations behind us. The origin of life is one of the strongest candidates for a past filter. We know, from geochemical evidence in ancient rocks, that life emerged on Earth remarkably quickly after the planet cooled enough to support it. Within the first 500 million to 800 million years of Earth's existence, possibly much faster. On a geological timescale, this is extremely fast. But fast given that it did happen, doesn't tell us how probable the origin of life is per unit time in a favourable environment. The probability of the first self-replicating molecule emerging from prebiotic chemistry is genuinely unknown. The simplest RNA sequences capable of self-replication require dozens of precisely ordered nucleotides. The probability of those assembling spontaneously in the right configuration in even the most chemistry-rich early ocean is not obviously high. Some researchers argue that life's rapid emergence on Earth suggests a high probability given the right conditions. Others argue that we can't estimate the probability from a single data point, and that the very fact we exist to observe Earth's rapid abiogenesis is a selection effect. We could only ever exist on a planet where life emerged, regardless of how improbable that emergence was. This is a genuine scientific uncertainty, not a resolvable debate with current data. The origin of life could be the great filter. The emergence of complex cellular life, eukaryotes, cells with nuclei and organelles, is another strong candidate. For the first roughly 2 billion years of Earth's history, life was exclusively prokaryotic. Single-celled organisms without nuclei, without mitochondria, without the complex internal machinery that makes possible everything from fungi to plants to animals to us. The transition to eukaryotic life appears to have happened only once in Earth's history, roughly 2 billion years ago, in a specific event called the endosymbiosis, when an archaeon engulfed a bacterium and instead of digesting it, incorporated it as a permanent internal structure that became the mitochondrion. This event, the origin of the eukaryotic cell, may have been extraordinarily improbable. We have exactly one example of it on Earth, despite 2 billion years of opportunity, during which prokaryotes covered every surface and filled every ocean of the planet. In all that time, in all those trillions of individual organisms, the endosymbiotic event appears to have been unique, once, from which everything complex, every animal, every plant, every thinking being, subsequently descended. If that's right, the origin of the eukaryotic cell could be the great filter. Life might be common across the universe. Simple prokaryotic life, microbial mats, chemosynthetic bacteria. These might fill every habitable ocean on every rocky world in the galaxy. But complex life, the kind that requires a nucleus and mitochondria and the entire metabolic infrastructure that makes large energy-hungry organisms possible, that might be rare to the point of being unique. Sexual reproduction, multicellularity, the Cambrian explosion of body plans, the emergence of nervous systems. Each of these represents a major evolutionary transition that may have required extraordinary improbable events or specific conditions. Any one of them could be a filter. The emergence of human-level intelligence itself is a candidate. Of all the complex animals that have existed on Earth, only one lineage in only the last 300,000 years has produced language, technology, and science. Dolphins and crows and elephants are intelligent, but they haven't built radio telescopes. The specific combination of bipedalism freeing the hands for tool use, social structure enabling knowledge transmission, vocal tract anatomy permitting complex language, and the particular architecture of the human prefrontal cortex. This combination may be extraordinarily contingent, a product of specific evolutionary pressures at a specific moment in a specific lineage, unlikely to be reproduced elsewhere. The point is, there are many plausible filter locations behind us. Each one represents a step in our own history that might have gone differently, that goes differently on most worlds, leaving the galaxy mostly empty of intelligence at our level of development or beyond. If any one of these is the dominant filter, we should feel, cautiously, that the road ahead is more open than it is closed. But now, let's look at the candidate filters that lie ahead. Candidate filter locations ahead of us. The invention of nuclear weapons. We made them in 1945. We came within minutes of using them several times. If the typical technological civilization eventually destroys itself through nuclear exchange before achieving spaceflight, that would explain the silence. But as I noted earlier, 80 years and still counting, it feels less inevitable from the inside than the hypothesis requires. Runaway climate change. A civilization that burns through its planetary resources and alters its climate to the point of societal collapse before reaching the technological threshold for spaceflight or interstellar communication might be a common failure mode. The timescale between industrialization and either climate catastrophe or a clean energy transition is short, a few centuries at most. If most civilizations fail to make that transition, they might destroy themselves or regress before becoming detectable. Artificial intelligence. The development of general artificial intelligence is frequently cited as a potential existential risk, either through misaligned AI pursuing goals that are incompatible with civilization's continued existence, or through other catastrophic misuses of the technology. If the typical technological civilization develops AI roughly when we are developing it, and if a significant fraction of those civilizations experience an uncontrolled AI transition that ends them, this could be a filter. The deeply disturbing version of the ahead filter argument is this: whatever kills civilizations might be something we don't know about yet. Something that every technological civilization encounters at roughly the developmental stage we are at now, and almost none survive. Something that hasn't revealed itself to us because we haven't reached the relevant threshold yet. A physics discovery that inadvertently destroys the discoverers. A pandemic-class pathogen enabled by biotechnology. Something we can't anticipate because no one has survived it to transmit the warning. In 2023, a group of researchers at Oxford's Future of Humanity Institute published a reanalysis of the Drake equation, using explicit probability distributions for the uncertain parameters rather than point estimates. What they found, using a method called Bayesian analysis, was striking. When you properly account for the uncertainty in the parameters, when you don't just pick a best guess for each factor, but instead represent the full range of possibility, the probability that we are alone in the observable universe is not vanishingly small, as Sagan and others assumed. It is in fact quite substantial, possibly as high as 40 to 50%. The key insight was that the Drake equation parameters, when expressed as uncertainty ranges rather than fixed values, have a multiplicative effect on the uncertainty in the final answer. And the distribution of possible outcomes is not symmetric. There's a long tail toward extremely rare, meaning that when you integrate over all possible values of the uncertain parameters, a large fraction of the probability mass ends up at very few civilizations. The Fermi Paradox may not require a filter at all. It may simply reflect the genuine possibility that we are among the first technological civilizations in the galaxy, and that the silence is not mysterious, it's expected. In 2023, a group of researchers at Oxford's Future of Humanity Institute published a reanalysis of the Drake equation, using explicit probability distributions for the uncertain parameters rather than point estimates. What they found, using a method called Bayesian analysis, was striking. When you properly account for the uncertainty in the parameters, when you don't just pick a best guess for each factor, but instead represent the full range of possibility, the probability that we are alone in the observable universe is not vanishingly small, as Sagan and others assumed. It is in fact quite substantial, possibly as high as 40 to 50%. The key insight was that the Drake equation parameters, when expressed as uncertainty ranges rather than fixed values, have a multiplicative effect on the uncertainty in the final answer. And the distribution of possible outcomes is not symmetric. There's a long tail toward extremely rare, meaning that when you integrate over all possible values of the uncertain parameters, a large fraction of the probability mass ends up at very few civilizations. The Fermi Paradox may not require a filter at all. It may simply reflect the genuine possibility that we are among the first technological civilizations in the galaxy, and that the silence is not mysterious, it's expected. But it is the direction of the filter that matters most, and it's worth being completely clear about what Hanson's framework implies for us, right now, practically. Here is the structure of the argument. Imagine a graph of probabilities. On one axis, you have the probability that the great filter is mostly behind us, that we've already survived the hard part, that the silence is explained by how rare our own developmental history is. On the other axis, you have the probability that it is mostly ahead of us. These two probabilities must add up to something close to 1. The question is, what should move our estimate? The answer, counterintuitively, is that finding life makes things worse, not better. Worse. Here is why. If we discover that life has independently emerged elsewhere, on Mars, on Europa, in the atmosphere of an exoplanet, that dramatically increases our estimate of the fraction of habitable worlds where life emerges, which means life being common is no longer available as a filter, which means whatever filter is making the galaxy quiet has to be somewhere else in the chain. And each time we discover that another step in the developmental pathway is common, that life emerges readily, that eukaryotic cells aren't unique to Earth, that complex multicellular life appears independently on multiple worlds, we are eliminating candidate filters behind us and pushing the great filter further toward our future. This is the most counterintuitive and deeply unsettling aspect of the Fermi Paradox. In a very real sense, each positive discovery in astrobiology, each sign of life elsewhere, makes the universe slightly more threatening, because it narrows down where the filter must be and it eliminates the reassuring possibility that the rare step is behind us. The most terrifying discovery we could make, from a purely Fermi Paradox perspective, would not be a dead universe. It would be a universe teeming with microbial life everywhere we look, with complex animals on some worlds, with the ruins of technological civilizations on a few, but with no surviving, transmitting, expanding civilizations. That pattern, life common, intelligence occasionally appearing, but nothing surviving, would be a screaming signal that there is a near universal filter ahead of us, a wall that civilizations hit and don't come back from. Every telescope we point at an exoplanet atmosphere, looking for oxygen or methane or other biosignatures, carries this double-edged quality. The discovery we most want to make, the discovery of life beyond Earth, might be the discovery we should fear most in this specific analytical framework. Not because life is bad, but because its commonness changes the math on where the filter is. There is one more aspect of the great filter argument worth spending time on, and it's one that Hansen himself has emphasized repeatedly in subsequent writing: the relationship between civilizational lifespan and the filter. Suppose the great filter is civilizational lifespan. Suppose the reason the galaxy is quiet is not that life is rare or intelligence is rare, but that technological civilizations are characteristically short-lived, that they reliably destroy themselves within a few thousand years of developing radio technology, too quickly to produce a detectable or persistent galactic signature. For this to explain the Fermi Paradox, you need civilizations to be very short-lived on average. Our own civilization has had radio technology for about 120 years. If the average civilizational lifespan is, say, 200 years after the development of radio, if civilizations typically destroy themselves within 1 to 2 centuries of reaching our level of technology, then at any given time in the galaxy's history, the number of simultaneously broadcasting civilizations is tiny. Most have already gone quiet, most haven't yet arisen. The few that currently exist are separated by vast distances, and their brief broadcast windows don't overlap. But here's what makes this version of the filter tractable in a way that is new in the last few years. We are, for the first time in our history, beginning to be able to do archaeology of extinct civilizations, not in our own solar system, not yet, but in exoplanet atmospheric spectra, because if a civilization burned through its resources rapidly, altered its planetary chemistry through industry, and then collapsed, those chemical signatures might persist in the atmosphere for millions of years after the civilization is gone. Atmospheric pollution, radioactive decay products of industrial-scale nuclear material, disruptions in the carbon and nitrogen cycles of a planet that once hosted a technological civilization. JWST is currently taking spectra of exoplanet atmospheres. It cannot yet detect the subtle signatures of industrial chemistry at interstellar distances. But the next generation of telescopes, the extremely large telescope currently under construction in Chile, the proposed Habitable Worlds Observatory, will have the sensitivity to do exactly this. We may, within the next 20 to 30 years, be able to look at the atmospheres of nearby Earth-like planets and see whether any of them bear the chemical scars of a civilization that rose and fell. If we find a graveyard, a planet whose atmosphere tells the story of a technological civilization that no longer exists, that would be confirmation that the great filter is ahead of us and that civilizations do fail. It would be the most haunting discovery in human history, and also one of the most important. If we look at hundreds of Earth-like planets and find none that bear those scars, that too is evidence that either civilizations are rare, or they somehow avoid the collapse scenario, or something else is happening. The great filter is testable. In a way it wasn't a decade ago, it is now testable. within the lifetimes of scientists working today. This Bayesian reanalysis is one of the most important developments in Fermi Paradox research of the last decade, and we're going to dig into it properly in a later chapter. But before we get there, we need to talk about something that happened in the last 3 years that has genuinely changed the texture of this conversation. We found some things out there, things that weren't supposed to be there, or that we weren't supposed to be able to find yet. And how you interpret those findings depends entirely on where you think the Great Filter is. End of part 1, continuing in part 2, chapters 4 through conclusion. Chapter 4, what we've actually found and why it matters. Let's talk about what has changed in the last 3 years. Because this isn't just a philosophical essay about a problem that has been stuck in the same place since 1950. The Fermi Paradox conversation has moved significantly. And the reason it has moved is that we now have data we didn't have before. Real observational data from instruments powerful enough to look at the atmospheres of planets orbiting other stars and say something specific about their chemistry. In 2021, the James Webb Space Telescope launched from the Guiana Space Center in French Guiana, folded into its rocket like a piece of origami, and began the most consequential astronomical mission of the generation. By the middle of 2022, it was operational and producing data, and within its first 2 years of science operations, it had already begun to change the terms of the Fermi Paradox discussion in a specific and important way. In September 2023, astronomers published a paper in the journal Nature Astronomy, announcing the detection of carbon dioxide and methane, and a tentative detection of something else, in the atmosphere of an exoplanet called K218b. K218b is a sub-Neptune world, larger than Earth but smaller than Neptune, orbiting a red dwarf star about 120 light-years from us in the constellation Leo. It sits in its star's habitable zone, the orbital distance range where liquid water can exist on a surface. The detection of carbon dioxide and methane was not itself surprising. Both molecules are known to exist in planetary atmospheres. What made the K218b paper globally significant was the tentative detection of a third molecule, dimethyl sulfide, DMS. A molecule that, on Earth, is produced only by biological processes, specifically by marine phytoplankton and other microorganisms. Abiotic, non-biological, production of DMS at detectable atmospheric concentrations has never been observed in a natural setting on Earth, and has no clear non-biological pathway in current planetary chemistry models. The DMS signal was tentative. The team was careful to say possible detection rather than confirmed detection. The signal was at roughly 3 sigma confidence, meaning statistically significant enough to take seriously, but not at the 5 sigma threshold that physicists conventionally require before claiming a discovery. The researchers were explicit that further observations were needed, and that the signal could potentially be explained by unknown abiotic chemistry. But here's what happened next. The DMS signal became one of the most discussed astronomical findings of 2023. Not because scientists were running headlines screaming "life found," but because the scientific debate about it revealed something important. The community had no good alternative explanation. Papers were published attempting to identify abiotic pathways to atmospheric DMS. None of them were compelling. The most rigorous abiotic chemistry models for K218b's specific atmospheric conditions suggested that DMS at the observed concentration was difficult to generate without biological input. This doesn't mean life has been detected on K218b. To be absolutely clear, it has not been confirmed. Science requires extraordinary evidence for extraordinary claims, and the K218b DMS detection is a signal in a spectrum, not a definitive proof of biology. K218b may be what its atmospheric composition suggests, a Hycean world, a planet covered by a global liquid water ocean under a hydrogen-rich atmosphere. But whether anything lives in that ocean is a question that will require years of additional observation to answer. What the K218b story tells us is not "we found aliens." It tells us something subtler and in some ways more important. We now have the capability to detect potential biosignatures in the atmospheres of planets 120 light-years away. A capability that did not exist 5 years ago. A capability that will improve as JWST accumulates more observation time and as next-generation observatories come online. We have entered the era of exoplanet atmospheric chemistry. We are now reading the air of other worlds. And that changes the Fermi Paradox conversation fundamentally, because for the first time, the question is not purely theoretical. We have a method of testing it. But K218b is not the only new piece of evidence. Let me give you the fuller picture of what's been found and what it means. In 2020, researchers announced the detection of phosphine, pH3, in the atmosphere of Venus, using the James Clerk Maxwell Telescope and the ALMA Radio Telescope Array. Phosphine is, like DMSAM, a molecule that has no known abiotic atmospheric production pathway in the quantities suggested by the initial observations. On Earth, it is produced by microbial life in anoxic, oxygen-free, environments and by human industrial activity. In Venus's sulfuric acid clouds, where temperatures and pressures are in a range that isn't immediately lethal, there was an initial claim of a biosignature. The Venus phosphine story became messier than K218b. The signal was challenged by multiple teams who reanalyzed the data and suggested the initial detection had overestimated the concentration. Some teams reduced the claimed phosphine concentration by factors of 7 or more. The calibration of the telescope data was called into question. By 2022, the consensus had shifted toward marginal detection at best, possibly noise. The Venus phosphine story was not a confirmed biosignature. It was a contested signal that highlighted the difficulty of this kind of remote atmospheric chemistry measurement. But it also highlighted that the scientific tools for looking at these questions are improving rapidly enough that genuine detections and false positives are both going to happen. The methodology is being stress tested in real time, and the fact that the community mobilized so quickly to rigorously challenge the Venus phosphine claim is itself a sign of health in the field. The standards are high, the scrutiny is fierce, and the desire to avoid confirmation bias is genuine. There was also the JWST carbon dioxide detection in the atmosphere of WASP-39b in 2022, the first direct detection of CO2 in an exoplanet atmosphere. Not a biosignature in itself, but a demonstration of the precision with which JWST could analyze atmospheric chemistry, and a proof of concept for the biosignature searches that would follow. And then there's what's happening in our own solar system, because the solar system searches have been producing results that complicate the picture in interesting ways. NASA's Perseverance rover, which has been exploring the Jezero crater on Mars since February 2021, has found something that surprised the science team: organic molecules. Specifically, it has found aromatic organics and aliphatic carbon compounds preserved in ancient lakebed sediments that date to roughly 3.5 billion years ago, when Mars had liquid water on its surface. These are not confirmed biosignatures. Organic molecules can form through non-biological chemistry, but they are the prerequisite chemistry for life, preserved in a location where liquid water once existed, at a time when Mars's climate may have been habitable. The Perseverance sample return mission, which will eventually bring these samples to Earth for detailed laboratory analysis, is the most consequential planetary science mission of the current decade. Because laboratory analysis of those samples, with instruments far more sensitive than anything we can land on Mars, might reveal whether the organic chemistry in those rocks is biological or abiotic in origin. Not definitely, not certainly, but possibly. We are at a moment in scientific history where multiple lines of evidence — exoplanet atmospheric chemistry, Mars geology, the subsurface oceans of Europa and Enceladus, the organic rich lakes of Titan — are converging simultaneously on the question of life beyond Earth. Not any single one of them is conclusive, but their convergence, their collective weight, is shifting the probability distribution in ways that matter for how we think about the Fermi Paradox. Here is the key point. The Fermi Paradox operates on a specific assumption about the distribution of life in the universe. It assumes that life is common enough and intelligence frequent enough that we should by now have detected something. If the new data suggests that life, even microbial life, is actually rarer than we thought, that directly changes the mathematics of the paradox. If, on the other hand, we find biosignatures on K218b, or organics in Mars samples, or evidence of life in Europa's ocean, that changes it in the other direction, and, as I explained in the Great Filter chapter, in a direction that should give us pause. The data is not in yet, but it is coming, and the rate at which it is coming is accelerating in a way that justifies the specific excitement of this moment. There's one more recent development that I want to bring into this chapter, because it doesn't get nearly enough attention in mainstream coverage of the Fermi Paradox, and it is genuinely one of the most significant things that has happened in CT in decades. In April 2024, the Breakthrough Listen initiative published an analysis of data from the Meerkat radio telescope array in South Africa, one of the most sensitive radio telescope arrays in the world. The analysis surveyed 820 nearby star systems for radio signals consistent with artificial transmission. The result? No confirmed detections. But in the methodology paper, the team disclosed something that should be read carefully. The survey covered 820 stars out of approximately 100,000 Sun-like stars within 100 light-years of Earth. It covered a specific frequency range, roughly 1 to 4 GHz, and a specific set of signal types. It was sensitive enough to detect a transmitter of roughly 10 megawatts from 100 light-years away, which means a transmitter comparable to our most powerful radar installations. A civilization with our level of technology actively beaming a signal at us would have been detectable, nothing. But 820 stars out of 100,000 is 0.8% coverage of the nearby stellar neighborhood. In frequency space, 1 to 4 GHz is a fraction of the full radio spectrum. In signal type space, the survey focused on narrowband continuous wave signals, one of many possible communication schemes. The survey tells us, we haven't detected a signal with these specific characteristics from these specific stars in this specific frequency range. It does not tell us the full SETI search space has been covered. Far from it. Our total SETI search coverage, even after 65 years, is estimated to be equivalent to searching a hot tub's worth of water, when the question is whether there are fish in the Earth's oceans. This doesn't mean SETI is pointless. It means SETI is just beginning, in terms of meaningful coverage. And the tools we now have, from JWST to Meerkat, to the upcoming Square Kilometre Array, which will be orders of magnitude more sensitive than any previous radio telescope, mean that the coming decade will see more search coverage than all previous SETI history combined. We are not at the end of the search. We are at the beginning of the era when the search becomes serious enough to produce meaningful constraints. We are not at the end of the search. We are at the beginning of the era when the search becomes serious enough to produce meaningful constraints. There is also a category of search that is often overlooked in popular coverage of SETI, and it's one that has gained significant scientific attention in the past 5 years. The search for techno-signatures that don't require a civilization to be intentionally broadcasting. The concept of a Dyson sphere, a structure built around a star to capture most or all of its energy output, was first proposed by physicist Freeman Dyson in 1960. A full Dyson sphere would be almost inconceivably large, but even a partial Dyson structure, a cloud of solar energy collectors surrounding a significant fraction of a star's surface, would produce a distinctive infrared signature. The star's visible light output would be reduced, while its infrared emission, waste heat from the collectors, would be increased. This spectral anomaly would be detectable from Earth with current telescope technology. In 2015, astronomer Tabitha Boyajian and collaborators announced the discovery of a star known as KIC8 462852, now nicknamed Tabby's star, which showed unusual and irregular dips in brightness that couldn't be explained by any known natural process. For a brief exciting period, one of the most frequently cited explanations was a partial Dyson structure in construction. The media ran wild with it. Subsequent observations revealed that the dimming was most likely caused by a swarm of dust and irregular debris, possibly the remnants of a disrupted comet family. The Dyson sphere hypothesis faded, but the episode was important because it demonstrated that the search for megastructures is not purely theoretical. It is a real observational program that can be applied to existing telescope data, and that the universe is large enough and strange enough to produce anomalies that require investigation. The Gaia Space Telescope, which has mapped the positions and brightnesses of nearly 2 billion stars in the Milky Way, represents a dataset in which Dyson structure candidates could in principle be systematically identified. Researchers have begun doing exactly this, running statistical analyses of the Gaia catalogue looking for stars with anomalous infrared excesses consistent with partial energy capture. So far, no confirmed technosignature, but the search is only beginning. There is also the emerging field of atmospheric pollution signatures, The idea that industrial chemistry leaves traces in a planet's atmosphere that are distinct from biology. Nitrous oxide from agricultural and industrial processes, chlorofluorocarbons from refrigeration, specific isotopic ratios of carbon dioxide from fossil fuel burning. These signatures might persist in a planetary atmosphere for thousands to millions of years after a civilization has collapsed or transformed. Detecting them would not tell us that a civilization currently exists on the planet, but it would tell us that one existed at some point. It would be, effectively, reading the tombstone. The next generation of telescopes will have the sensitivity to search for these signatures. The extremely large telescope, with its 39-meter primary mirror, is designed in part to characterize the atmospheres of Earth-like planets in detail. The proposed Habitable Worlds Observatory, currently in the concept phase at NASA, would be specifically designed to image and characterize Earth-like planets around nearby stars. We are building the tools to not just search for life, but to search for the ruins of civilizations, and whether we find ruins or silence or signatures of the living, each result is a data point that moves our understanding of the Fermi Paradox forward. Chapter 5: The Dark Forest. The theory that actually keeps scientists awake. In 2008, Chinese science fiction author Liu Cixin published the second volume of what would become the Three-Body Problem trilogy. In it, he formalized what is now known as the Dark Forest theory, a proposed solution to the Fermi Paradox that is distinctive in its internal consistency and in its ability to explain not just the silence, but the form of the silence. The Dark Forest theory begins with two axioms. First, all life desires to survive. Second, the total resources in the universe are finite. From these two premises, Liu derives a chain of logic that produces a deeply uncomfortable conclusion about the behavior of civilizations encountering each other. The argument goes like this: any civilization that encounters another faces a fundamental uncertainty problem. They cannot know whether the other civilization is benign or hostile. They cannot know what the other civilization's future capabilities will be, because technological development is rapid and unpredictable. Even a currently weaker, less advanced civilization might surpass a stronger one in a brief period. And crucially, they cannot communicate reliably enough to resolve this uncertainty. Because any communication is slow over interstellar distances, any agreement made could be broken by the time the light carrying the reply arrives, and the other civilization's internal politics and values might change entirely in the meantime. In this situation of irreducible uncertainty, a civilization has two options: make contact and trust that the other civilization is benign, or destroy the other civilization before it can potentially become a threat. And the logic, given finite resources and the assumption that any civilization that knows about you is a potential threat, pushes toward preemptive destruction. The dark forest of the title is the universe itself, a dark forest in which every civilization is a hunter, moving silently, unwilling to reveal its presence, because any revealed presence invites discovery and potential destruction by something bigger and more capable. Civilizations that broadcast their existence are eventually eliminated by those that don't. The survivors are the silent ones. The universe converges towards silence because silence is the evolutionarily stable strategy in a universe of competing, resource-limited civilizations. The dark forest theory is fiction, but it has been taken seriously enough by scientists and philosophers to generate a genuine debate in the astrobiology literature about whether it is a plausible real-world explanation for the Fermi Paradox. And the debate reveals some interesting tensions. The theory has real strengths. It explains the uniformity of the silence, not just that we haven't detected signals, but that we haven't detected any signatures of intelligence anywhere in the observable universe. If civilizations actively suppress each other, you'd expect silence, even if civilizations were common. It provides a mechanism, predatory suppression, that could maintain the silence consistently across billions of years of galactic history. It also, disturbingly, provides a specific prescription for what we should do as a civilization: stop broadcasting. We have been broadcasting our existence since the first radar pulses in the 1930s, and the first deliberate messages like Voyager's Golden Record and the Arecibo message. If the dark forest theory is correct, we've been screaming our location into a predatory universe for nearly a century. There have been serious scientific discussions, not fringe discussions, but discussions in journals and at academic conferences, about whether we should implement a policy of radio silence for Earth, and whether deliberate messaging of alien civilizations, called METI, Messaging Extraterrestrial Intelligence, should be banned or regulated. Stephen Hawking was among those who publicly argued against broadcasting our existence. In a famous 2010 documentary, he compared the encounter between humans and an alien civilization to the encounter between Columbus and the Native Americans, and noted that it didn't go well for the Native Americans. The counter-argument is that our radio leakage has been propagating outward for nearly a century. Any civilization within 100 light-years that has the technology to detect radio signals already knows we're here. The horse is already out of the barn. A policy of radio silence now would be too late to prevent detection and would only prevent intentional communication, which might actually be in our interest to attempt. The deeper problem with the dark forest theory, as a scientific explanation for the Fermi Paradox, is that it requires a very specific assumption about civilizational values, that all sufficiently advanced civilizations adopt a fundamentally predatory stance toward others. This requires that the development of advanced intelligence consistently leads to defection rather than cooperation in a cosmic prisoner's dilemma. But here on Earth, the development of advanced intelligence has produced imperfectly, messily, with enormous amounts of violence along the way, increasing cooperation, larger and larger coalitions of people operating under shared rules and institutions, nation-states, international law, global trade, the scientific community. These are imperfect institutions with constant violations, but the trend over centuries has been toward more cooperation rather than less, despite the fact that competition and conflict remain constant. If intelligence tends toward increasing cooperation within a species, it's not obvious why it would tend toward predation between species. The resources in the universe, while finite in principle, are so vast relative to any civilization's actual need that the motivation for resource-based conflict between stars seems questionable. A civilization capable of traveling between stars is, by definition, capable of harvesting the resources of its own stellar neighborhood, which represents effectively unlimited energy and matter for any reasonable definition of enough. The dark forest theory is a brilliant piece of science fiction. As a scientific hypothesis, its internal logic holds, but its first principles are contestable. Whether it describes the real universe depends on assumptions about the values and motivations of advanced civilizations that we have no way to test. But there is one version of the dark forest adjacent idea that is more tractable and more specifically disturbing, and it's one that has been discussed with more rigor in recent academic literature: the predator civilization model. Rather than positing that all civilizations are predatory, the predator civilization model suggests that the Fermi Paradox could be explained by a single, very old, very advanced civilization that has taken a systematic approach to suppressing competitors. One civilization, the first one to reach galaxy-scale capability, could in principle ensure its own long-term survival by systematically identifying and eliminating any other civilization that approaches a dangerous level of capability. This doesn't require every civilization to be predatory. It only requires one, the first one. A single civilization with a billions of years head start and the motivation to remain the dominant intelligence in the galaxy could maintain that dominance indefinitely, clearing the competition as it arises, using detection methods far more sensitive than anything we have, acting on timescales far shorter than anything we could respond to. This model is sometimes called the Berserker hypothesis in its most extreme form, after the idea of autonomous self-replicating machines programmed by a long-dead civilization to destroy any other civilization that reaches a certain technological level. It was formalized by astronomer Fred Saberhagen, and it has the advantage of explaining both the silence and the absence of any evidence of a colonizing civilization. The colonizing civilization is there, but it is specifically designed to be invisible until it acts. The Berserker hypothesis is unprovable and unfalsifiable in most formulations, which limits its scientific utility, but it is worth naming because it represents the most extreme version of the filter ahead of us idea. Not a natural filter, not a self-destructive tendency, but an active, technological, engineered filter that identifies civilizations and removes them before they become capable of independent expansion. If something like this exists, we have been broadcasting our location for 90 years. The nearest stars are 4 light-years away. We are, on the cosmic scale, advertising our presence with increasing loudness. Whether that matters, whether there is anything in the galaxy that cares about our broadcasts, is a question that may answer itself in time. In the meanwhile, the debate about METI policy continues, the radio silence advocates grow more vocal, and the question of whether contact or concealment is wiser remains one of the most genuinely consequential open policy questions in science. Chapter 6. The Math That Changed Everything. Let's get specific. Let's talk about the Oxford paper, because it deserves more attention than it typically gets in popular science coverage of the Fermi Paradox, and because it represents the most rigorous mathematical treatment of the problem to date. In 2018, Anders Sandberg, Eric Drexler, and Toby Ord at Oxford University's Future of Humanity Institute published a paper titled Dissolving the Fermi Paradox. The title is deliberate. Not solving, dissolving. Their claim was not that they had found the answer, but that they had demonstrated the paradox was less paradoxical than it appeared, that it was the product of a specific mathematical error in how the Drake equation had been traditionally applied. The error was this: previous treatments of the Drake equation had chosen point estimates for the uncertain parameters and multiplied them together to get a final number of expected civilizations. But the parameters in the Drake equation are not known quantities with small error bars. They are deeply uncertain quantities with ranges that span many orders of magnitude. The fraction of habitable planets where life emerges could be anywhere from essentially 1, life emerges almost everywhere it can, to essentially 0, life is so improbable that Earth is alone in the observable universe. The fraction of life-bearing worlds where intelligence emerges could be similarly anywhere on the spectrum. When you multiply several very uncertain quantities together, you don't get a number, you get a distribution, and the shape of that distribution matters enormously. If the distributions are skewed, if there's more probability mass at close to 0 than at large numbers, which there is for biological probability estimates, then the expected value of the product is dominated by the low tail. Most of the possible universes implied by the uncertainty in our parameters are universes where technological civilizations are extremely rare or unique. Sandberg, Drexler and Ord went through the current scientific literature on each parameter in the Drake equation and characterized the uncertainty range for each, using probability distributions derived from actual research rather than guesses. The result was striking. When they propagated the uncertainties through the full calculation, they found that there was a roughly 30 to 50% probability that we are alone in the observable universe, meaning the entire Hubble volume, roughly 93 billion light-years across. Not just alone in the galaxy, potentially alone in the observable universe, and critically, they found that the Fermi Paradox, the apparent contradiction between the expected number of civilizations and the observed silence, largely disappears when the uncertainties are properly accounted for. The silence is not surprising if our estimates of the relevant probabilities are even modestly pessimistic. A universe in which we don't detect alien intelligence is fully consistent with the uncertainty in our understanding of how life and intelligence emerge. This doesn't mean we're alone. It doesn't mean intelligent life is rare. It means we have far less epistemic justification for expecting the universe to be full of communicating civilizations than was commonly assumed in earlier treatments. The Fermi Paradox in its classical form was based on a kind of false precision, an overconfidence in optimistic parameter estimates that, when properly expressed as distributions, don't actually predict the teeming cosmos Sagan described. The implications of the Oxford paper are profound and have not been fully absorbed by the broader culture. The mainstream narrative about the Fermi Paradox continues to assume that aliens should exist, and we just haven't found them yet. The Oxford paper says, actually maybe not. Maybe the prior probability of being alone is much higher than people assume, and we shouldn't be surprised by the silence. This is not a comfortable conclusion. Being alone, genuinely alone, or among the first, or one of a very small number of technological civilizations in the entire observable universe, carries its own kind of existential weight. There is something bleak about a universe 93 billion light-years across that contains, in all its 200 billion galaxies, only one species capable of asking questions about it. But there is also something extraordinary about it. If we are among the first, if the silence reflects genuine cosmic earliness rather than a great filter or a predatory universe, then the responsibility we carry is almost incomprehensible. We are not a footnote, we might be the beginning. Everything that intelligence will ever do in this universe might trace back to what we do here, on this small planet, in this early moment of cosmic time. There is a name for this scenario in the academic literature. It's called the rare intelligence hypothesis, and it differs from the rare earth hypothesis in an important way. Rare earth says the conditions for complex life are uncommon. Rare intelligence says something slightly different, that even given complex life, the emergence of reflective technological intelligence is extraordinarily improbable, and that its probability is not well predicted by evolutionary success in a general sense. Intelligence is not the inevitable endpoint of evolution. It is one of many possible adaptive strategies, and the specific combination of cognitive capacities, language, cumulative culture, abstract reasoning, tool use, that produce technological civilization in humans may require conditions so specific that it has happened perhaps once, or a handful of times, in the current history of the observable universe. There is one more mathematical development that deserves mention, and it's more recent than the Oxford paper. In 2021, astrophysicist David Kipping at Columbia University published an analysis attempting to constrain the probability of abiogenesis, the origin of life, from the single data point of Earth. His approach was Bayesian. Given that we exist to observe Earth, and that life emerged relatively quickly in Earth's history, what can we infer about the underlying probability of life's emergence per unit time in a habitable environment? His analysis produced a result with very wide error bars, as expected from a single data point, but with a moderately optimistic central value. The probability of abiogenesis given a habitable environment with sufficient time is more likely than not to be above 10% per billion years. This is consistent with life being common in the universe without requiring it to emerge nearly everywhere. It means the filter for life's origin is probably not where the great filter is. It supports the idea that simple microbial life may be widespread while complex technological intelligence remains rare. Put the Oxford parameter uncertainty analysis together with the Kipping abiogenesis estimate, and the picture that emerges is this. Simple life is probably common. We would not be surprised to find bacterial-level life in Europa's ocean, or remnant chemistry of life on Mars, or biosignatures in the atmospheres of a fraction of habitable exoplanets. But the path from simple life to technological civilization is almost vanishingly improbable, containing one or more steps of extraordinary difficulty, and the expected number of current technological civilizations in the galaxy may be very small, possibly including only ourselves. This is the picture that the new mathematics gives us. It is not the picture of a cosmos teeming with intelligence. It is not the picture of cosmic loneliness. It is the picture of a universe in which the emergence of technological intelligence is a rare and recent event, in which we may be among the first, and in which the question of what comes next depends almost entirely on what we do. Chapter 7. The answer that changes everything we've been building toward this. Let's put the full picture together and ask the question directly. Has the Fermi Paradox been solved? Not definitively. Science doesn't usually work that way. There is no single paper, no single discovery, no revelation from a first contact event that has provided a clean resolution. But what I am arguing, what the accumulated evidence and mathematics of the last decade suggest, is that the Fermi Paradox is dissolving. Not in a dramatic, paradigm-shattering way, but in the quiet way that many great scientific puzzles dissolve, through the patient accumulation of evidence that changes the probability distribution of the question. Here is the most likely resolution, as best as the current state of knowledge allows. It is a combination of several factors, each of which independently reduces the expected number of detectable civilizations, and which together bring that expected number close to or below 1. First, the universe is younger than the Fermi Paradox conventionally assumes. Yes, the universe is 13.8 billion years old. Yes, the first stars formed within the first few 100 million years, but the first generation of stars were composed almost entirely of hydrogen and helium, the elements produced in the Big Bang. They had essentially no carbon, oxygen, nitrogen, phosphorus, or any of the other heavy elements that biochemistry requires. Those elements, collectively called metals in astronomical jargon, had to be forged in the cores of those first stars and distributed through the galaxy in supernova explosions. The next generation of stars formed from that enriched material still had relatively low metallicity compared to the Sun. Only after several generations of stellar birth and death, a process that took several billion years, did the galaxy have enough heavy elements in enough regions for Earth-like carbon-rich planetary chemistry to be possible. By the standards of galactic chemical evolution, Earth is not late, it's arguably early. The conditions for rocky, carbon-rich, ocean-bearing planets in the right stellar neighbourhoods to become genuinely widespread may be only now reaching their peak. Our galaxy is still forming stars, still evolving chemically, still becoming a more hospitable place for the specific chemistry of biological life. The window for civilizations like ours is only a few billion years old, not 13 billion. Second, the transition from microbial life to complex life appears to be extraordinarily improbable. The evidence for this is the Earth itself. Our planet had simple microbial life within its first billion years of existence. It then remained at approximately that level of complexity for 2 billion years. 2 billion years during which conditions were broadly hospitable, during which chemistry was running continuously, during which enormous numbers of individual organisms existed and evolved, and during which nothing more complex than simple prokaryotes emerged. 2 billion years of stagnation in biological complexity. Then, in a relatively brief interval, the eukaryotic cell emerged, and from there the Cambrian explosion of body plans within a few 100 million years, and then complex animals, and then eventually us. The timeline suggests that the barrier between simple life and complex life is not easily cleared. Earth cleared it, but it required 2 billion years of waiting for a specific improbable event, and that event appears to have happened only once. Third, the specific combination of conditions that produce technological intelligence on Earth may be unique in ways we are only beginning to characterize. The stability of Earth's climate over 3.5 billion years, enabled by plate tectonics and the carbon cycle, the specific mass of the Moon and its effect on axial tilt stability, the location of the solar system in the galactic habitable zone, the specific sequence of evolutionary contingencies that led from the first animals to the first hominids to Homo sapiens and the cognitive revolution of roughly 50,000 years ago. Any of these could be a rare conjunction, and their product could be rarer still. Fourth, technological civilizations may be inherently short-lived in ways that prevent simultaneous coexistence with others. Not because they inevitably self-destruct, but because the window between detectable and galaxy colonizing might be very narrow, a few thousand years or a few tens of thousands, and the probability of two civilizations being in that window simultaneously, in a galaxy where conditions for technological life have only recently been adequate, may be very low. Fifth, the Great Filter may have multiple components, all located partially behind us and partially ahead, rather than being a single wall. The aggregate effect of several moderately improbable steps, each one a factor of 100 or 1000, rather than a single factor of a trillion, could produce the same silence without requiring any one catastrophic barrier. We don't need a single Chicxulub-level improbability in our past. We need the product of several moderately improbable things to be very small. And given how many steps separate a rocky planet from a transmitting civilization, that product may be small enough to explain our solitude. Sixth, there is one more factor worth naming that rarely appears in popular treatments of the Fermi Paradox: the observation selection effect, or what philosophers call the anthropic principle. We can only observe the universe from a planet where the conditions allowed observers to evolve. This is not a statement about what kind of universe exists, it's a statement about what kind of universe we could possibly be observing from. Even in a universe where the vast majority of habitable planets never produce intelligence, the rare planets that do produce intelligence would always find themselves to be the exception, looking out at a mostly empty cosmos and wondering why. Nick Bostrom, the Swedish philosopher, has written extensively about the interaction between the anthropic principle and the Fermi Paradox, and his analysis suggests something important. The fact that we exist to observe the universe cannot be used as evidence that intelligence is common. Of course, we find ourselves in a universe that allowed our existence. That's trivially guaranteed by the fact that we exist. What it doesn't tell us is whether universes or galaxies that allow our kind of existence are common or rare. The anthropic, principle doesn't solve the Fermi Paradox, but it does caution against a specific kind of overconfidence, the assumption that because we exist, and because we find the conditions for life apparently widespread, that the full chain from conditions to life, to intelligence to technology must therefore be common. That inference doesn't follow. The conditions for life can be common, while the full chain remains extraordinarily improbable. And we, standing at the end of the chain, can't use our existence to argue about the probability of that chain, because we would have to be here to ask the question regardless. Seventh, and finally, the universe's age distribution matters. Of all the stars in the Milky Way that will ever form and host potentially habitable planets, we are observing the galaxy at a relatively early point in that distribution. The Sun is roughly 4.6 billion years old in a galaxy 13.6 billion years old, but the galaxy will continue forming stars for another 10 to 100 billion years. The lifetime of the Milky Way as a star-forming galaxy extends far into the future. If technological civilizations become more common as the galaxy ages, as metallicity increases, as stellar populations become better distributed, as the universe becomes more chemically rich, then we are observing at a moment when civilizations are relatively rare simply because the galaxy is still early in its most productive phase. Most civilizations that will ever exist in the Milky Way have not yet been born. When you add all of these factors together, the recently adequate galactic chemistry, the improbability of complex life, the contingency of intelligence, the narrow broadcast window, the multiple partial filters, the anthropic selection effect, and the early cosmic moment, the expected number of detectable civilizations in the Milky Way at this moment may be very close to 1, possibly less than 1, which means we should not be surprised by the silence. We should not feel that it implies a dramatic explanation. The silence may simply be the expected condition of a universe that is, at this particular moment in its history, producing technological civilizations for the first time. This is the Fermi Paradox dissolving. Not with a definitive answer, but with the recognition that the apparent contradiction between the universe is big and old and we're alone is less sharp than it seemed once you carefully account for the specific chemistry, the specific timing, and the specific improbabilities involved in the path from matter to mind. But dissolving a paradox is not the same as answering all its questions, and there are two specific discoveries that could still dramatically change everything. The first is a confirmed biosignature in an exoplanet atmosphere. If JWST confirms the DMS signal on K2-18b, or if it detects oxygen and methane, a combination that strongly implies biological production, on a nearby Earth-like planet, that discovery would confirm that life emerges in more than one place in the galaxy, which would dramatically change the probability estimates and push the Great Filter further toward our future. It would make the silence more puzzling, not less. It would tell us that life is common and intelligence is still somehow missing, which would be, from the Great Filter perspective, a darker message than the one the math currently suggests. And here is a specific scenario worth sketching out, because it illustrates the stakes. Suppose JWST, in the next few years, confirms oxygen and methane in the atmosphere of Proxima Centauri b, the nearest known exoplanet, orbiting the nearest star, just 4.2 light-years away. Suppose the signal is unambiguous. Suppose the community converges on the interpretation that the most parsimonious explanation is biological production. That discovery would be the most significant scientific announcement in human history. It would be on every front page on Earth. It would initiate a philosophical and cultural reckoning that would take generations to fully absorb. The implications for religion, for philosophy, for ethics, for the question of what human life means, would be seismic, and it would make the Great Filter more frightening, not less. Because if life has independently emerged on Proxima Centauri b, 4 light-years away in our own cosmic backyard, life is not merely common in an abstract statistical sense. It is here, next door, practically a neighbour. And if life is that common, and the galaxy is still silent of technology, then the step between life and civilization is where almost everything is dying. Something ahead of us. Something we haven't encountered yet. Some wall that every civilization finds sooner or later, and that almost none of them come back from. The question of where the Great Filter is would transform, overnight, from an abstract philosophical puzzle to an urgent practical concern. What are we approaching? What is the thing that is killing them? What should we be looking for, preparing for, guarding against? That is the world in which a biosignature discovery on a nearby exoplanet lands. Not a world of celebration, at least not purely. A world of celebration shadowed by a very specific and very rational fear. The second is a confirmed artificial signal, a radio or optical transmission that cannot be explained by any natural process. This would of course be the most spectacular possible discovery and would instantly dissolve the Fermi Paradox in an entirely different direction. We are not alone, and something is transmitting. Where it fits in the great filter framework would depend entirely on the apparent age and nature of the civilization sending it. Until either of those discoveries happens, we are living in the most interesting moment in the history of this question. We have, for the first time, the tools to actually test the assumptions of the Fermi Paradox. We can measure exoplanet atmospheres. We can do radio surveys of unprecedented sensitivity. We can analyse the chemistry of Mars rocks in Earth laboratories. We can model the probability distributions of the Drake equation parameters with actual data rather than guesses. The answers are coming. Not all of them. Not soon enough for impatience, but they are coming. Conclusion. Let's go back to where we started. 4 physicists walking to lunch in the summer of 1950. 3 of them talking, one of them going quiet and then asking the question that has haunted every thinking person who encountered it since. Where is everybody? We've been sitting with that question for 75 years. We've proposed dozens of answers. We've built telescopes and launched spacecraft and written equations and run simulations and held conferences. And we've emerged from all of that effort with something that isn't quite an answer, but is more than we had before. Something that might be the shape of an answer, visible through the fog. The universe is 13.8 billion years old, and it is almost certainly too young, for its specific chemistry, to have produced many civilizations like ours. Life may be scattered across the galaxy in microbial forms, in deep subsurface oceans, in organic-rich clouds, in the margins of habitable worlds. But the path from microbe to mind is extraordinarily long and extraordinarily contingent and extraordinarily improbable in the specific ways that matter. We may be among the first, not the first absolutely, not necessarily the first sentient beings in any form in any corner of the universe, but possibly the first, or among the first, to reach this specific developmental stage in this specific region, of this specific galaxy, in this specific cosmic moment. That thought carries a weight that is difficult to fully absorb. Because if it's true, if the silence is the silence of an early universe, a universe that has just recently become chemically and thermodynamically capable of producing minds, then what we do next is not just the concern of our civilization. It is the concern of the universe. Everything that intelligence will ever make, every question it will ever ask, every discovery it will ever achieve, every form of beauty and meaning it will ever create, all of it traces back through a chain of improbable steps to this planet, this species, this moment. That is either the most inspiring or the most terrifying thought available to us, depending on how you look at it. Possibly both simultaneously. The Fermi Paradox has not been solved in the sense of a confirmed final answer, but it has been clarified. The mathematics has sharpened, the assumptions have been tested, the question has been asked more carefully and answered with more precision than was possible before, and what the careful answer suggests is this: the silence is expected. Not because the universe is hostile, or because we are alone in any absolute sense, or because something terrible is waiting ahead of us, Zobatsam. Though none of those can be ruled out, but because the universe is early, because we are early, because the process that produces creatures capable of asking where is everybody is rare enough and recent enough that there may not yet be many of them anywhere. Where is everybody? Possibly not yet. Possibly in the first moments of their existence, on planets we can now see with our telescopes, living lives too simple to transmit and too short to last. Possibly behind us in time, in the ruins of civilizations that rose and fell before the galaxy was old enough to remember them, and possibly, this is the thought that I want to leave you with, possibly coming, possibly not yet born, possibly the descendants of microbial life that is right now persisting in the warm liquid dark of Europa's ocean, beginning the first tiny steps of the multi-billion-year journey that eventually produces minds. The universe is 13.8 billion years old, and intelligence in it may be very new. We may be, in the most literal sense, pioneers, not the colonists of a well-mapped world, but the first explorers of a territory that has never been inhabited. The first ones to ask the questions, the first ones to build the telescopes, the first ones to sit around and wonder what is out there, and then actually go and look. The silence isn't a void, it's a canvas. What happens next depends on what we do with it.